All right, sound check, sound check. I can hear audio coming in just fine. Now let's switch to our camera and make sure that's working. Do I see movement on the screen? Yes, I do. Okay, then we are good to go. Let me put away my headphones so we can get started. All right, it's the moment you've all been waiting for. Well, maybe some of you haven't been waiting for this moment. Maybe some of you have been dreading this moment, but it's finally time to talk about what I consider to be the most important chapter in all of physics. It is time to talk about the topic of force, or dynamics as the AP course description likes to call it. Because, we have to make it sound all cool and stuff. Okay, force. So the plan for today is pretty much what I said at the end last time, although I think I did miss a few things. So we're going to go over, of course, definitions and all that. We're going to cover Newton's first law and probably get into Newton's second law as well. We're going to discuss a few types of forces. Well, I'm going to give a general overview of all the forces that we will see in AP Physics 1 and AP Physics C, except for the buoyant force, which you will see in Physics 1 for our last chapter on fluids. That I'm going to leave out, and I'm also leaving out the force of air resistance for now. For now, I'm just going to focus on a list of 7 forces that are used much more commonly in both Physics 1 and Physics C, and we'll deal with any other forces later when we get to them. So, other than that, what else are we planning for today? So, I'm going to cover those 7 forces kind of briefly, just briefly touch on them, and then over time we're going to cover each of those forces in a little bit more depth, and I believe I have 3 or 4 of them lined up for today. Last time I mentioned we'd be covering normal force, applied force, and tension force, and I would also like to cover gravitational force. That one should have been the first on the list. I don't know why I forgot to mention it last time. Well, maybe because I listed it last in the course plan, which again, I don't know why I did that. But yeah, other than that, if we have time, we are going to look at free body diagrams, which I think we're going to have the time for because I don't see it taking us that long to cover the basic ideas. Actually, let me see. What do I have as exercises lined up? I guess a review of just vector decomposition stuff. We might touch on that a little bit. And yeah, we're probably going to be doing force body diagrams, or free body diagrams, whatever you want to call them, today. Almost guaranteed that we're going to do it today because I don't see all the other stuff taking that long. And we might touch on some one-dimensional force problems. So without further ado, let's get started. What is force? So let's go with a definition. So, simple definition of force is a push or a pull. Force is a push or a pull. A push or a pull. Some of you have seen the Flipping Physics video introducing force, which I believe was one of the videos that I had in the course plan anyway. And yeah, I don't agree with Mr. P's definition. I understand where he's coming from. He's concerned about Newton's first law, so he defines force in a different way. He defines force as the ability to accelerate an object or something like that. And I don't think I don't think you need to word it that way. I think the simple definition of a push or a pull is all you need. Just because a force is applied to an object doesn't mean it's going to move. If I put this calculator here and I poke it, if I don't poke it hard enough, then it's not going to move. It's not going to accelerate. So I think that idea we already have from just everyday life. You can push on a wall as hard as you like. It's probably not going to move unless it's made out of some really flimsy material. So I think the simple definition of a push or a pull is all we need. A force is simply a push or a pull that may or may not cause something to accelerate. Emphasis on the word accelerate. Force does not cause motion, it causes acceleration, and that acceleration can cause motion for an object that we assume is initially not moving. Now, force falls into 4 categories. There are 4 different categories of forces, and this isn't really something you need to know for the AP exam, but I think it's helpful. So there's 4 categories for forces. There are 4 categories for forces, and those categories are contact forces, which are forces that are exerted by objects having physical contact with each other, contact forces. Things have to touch in order for these forces to act on them. 2 is, well, the opposite. No contact forces, or what are better known as field forces. Field forces do not require physical contact. For example, I'm sure we've all had the experience of playing with magnets. Magnets can push and pull each other without the need for any physical contact. If I hold 2 magnets far apart from each other, I have magnets. Where did I put them? Let me see if I can find them real quick. They're probably buried too deep into that drawer. I can't find them right away. Oh well, maybe next time. But yeah, things like the magnetic force, the electrostatic force, and even the force of gravity, right? Earth's gravity can pull on a satellite that's tens of thousands of miles up above Earth's surface, hovering in outer space. So those are all field forces. They do not require physical contact. And then the 3rd and 4th categories of forces we're not really going to deal with at all in AP Physics 1 or AP Physics C. Those would be weak nuclear forces and strong nuclear forces. Weak nuclear forces and strong nuclear forces, which you can study up on your own. You may have heard of at least the strong nuclear forces if you've done AP chemistry, or even just like honors chemistry. I'm pretty sure covers that stuff, unless the curriculum has changed that dramatically since I was last in high school. But yeah, strong nuclear forces are what keep the nucleus of the atom together. You know, you've got a whole bunch of protons bunched up in there. How come they don't just push each other outward? How come the atom doesn't just split itself due to all of that repulsion going on? Strong nuclear forces are responsible for that. And the weak nuclear forces are actually involved in the more violent type of nuclear force that you might think of when you hear the word nuclear. So yeah, there's some food for thought, but we are mainly going to be dealing with these first two. We are mainly going to be dealing with contact forces and field forces. And I feel like understanding that contact forces require physical contact while field forces don't, I think that understanding will help sometimes with some misconceptions that tend to happen, such as the idea that an object's weight can act on another object that it's physically in contact with. That's not true. If you put one object on top of another, if I put one calculator above another calculator, the weight of the top calculator is not what's being applied to this bottom calculator. It's a different kind of force, and in this specific scenario, it will be a force that's equal in amount to the weight of the top calculator, but that doesn't mean it's the weight. The weight is the force of gravity. The weight of an object is the force of gravity acting on an object, and that's a field force. That is between this calculator and the Earth, specifically like the Earth's core. Well, center of mass if we want to be super specific about it, but we'll define that term much later when we get to rotational dynamics. So yeah, the force of gravity is a field force. The force that this top calculator exerts on this bottom one, when it just sits on top of it like that, it's not a field force. It has to be some sort of contact force. So understanding those two categories of forces can help avoid these kinds of misconceptions, which are unfortunately common and even more unfortunately, in some cases, perpetuated by teachers. If only I was sitting in the room making decisions. I should probably run for school board or something like that. Oh, who am I kidding? I'm not going to have the time for that. Anyway, so we've covered our 4 categories of forces. Now, what do we have next? I guess it's time to talk about Newton's first law to understand what forces do. So, Newton's first law says, Newton's first law, which is also known as the law of inertia. All of Newton's laws have names when it comes to force. All of Newton's force laws have names associated with them. So Newton's first law is also called the law of inertia, and it says, I'm sure you've all heard it before, probably misused in that one stupid pharmaceutical advertisement about arthritis or whatever. Newton's first law: an object at rest tends to stay at rest and an object in motion tends to stay in motion with constant velocity unless acted upon by a net force. The key word net there I'm going to underline. So an object at rest tends to stay at rest and an object in motion tends to stay in motion, with constant velocity. Key term there, with constant velocity unless acted upon by a net force. Okay. So an object in motion tends to stay in motion with, I'm going to underline constant velocity. That's one of our important terms. And the other important term here is net force, not just unless acted upon by a force, but specifically, you need to act on an object with a net force in order to get the object to move if it's at rest, or to get the object to change its velocity if it's already moving. So let's talk about this a little bit more. Let's suppose we are far out in outer space. Let's suppose I'm far out in outer space. I'm not going to draw an astronaut suit, but let's say I have a box and I'm floating in outer space and I kick the box. I give the box a quick little kick, and then I let it go. And the box floats off into space, and it just continues in a straight line forever, unless it encounters like a planet or an asteroid or something with some sort of gravitational pull, or if it crashes into some other solid object on the way. But otherwise, what's going to happen is it's just going to float, and it's going to float with a constant velocity because there's no force on it. It'll just move with a constant speed and in a fixed direction, straight line. That is, if the net force on an object is 0, it will move in a straight line. If an object is moving, it will stay moving in a straight line until and unless some sort of force comes to alter its path. So objects, by default, if they are moving, they will move straight. If they are moving free from the influence of forces, they will just move straight. And they will not speed up, they will not slow down, they will just continue, I guess in our example, floating, drifting into space without ever stopping or turning or speeding up. Okay, so that's the first part, the constant velocity thing. So a lot of times students assume that there's no force on an object only when it's not moving, and if an object is moving, there must be a force on it. That's just not true. It's just that here on Earth, we don't really get to observe that because we don't have environments that are completely devoid of forces. But if we did have such an environment, like very far out in outer space, we'd be able to experience that very regularly. We'd be able to see that, yeah, when an object is just drifting through space, it doesn't need anything pushing or pulling on it to make it move in whatever direction it's moving. Okay, so constant velocity has been taken care of. What about this term net force? What does net mean? Those of you who have seen my, I want to say it was like my 3rd or 4th video in my chemistry playlist, have heard the term net ionic equations, and you've seen this example that I give for the term net. Let me actually go and grab, I think I actually have the same brand of product that I used way back then. Let me go grab that real quick. Here we go, my precious box of chamomile tea. So what you notice down here at the bottom is it says net weight 0.9 ounces or 25 grams. Now, we can forgive them for misusing the word weight. What they should be saying is mass, but nevertheless, net weight 25 grams. What does that mean? It means the 25 grams is how much the stuff inside the box weighs. They're not taking the box into account. Why would they? I'm trying to figure out how much stuff is inside the box. Counting the box as part of the total mass would just be cheating. It would be deceptive advertising, and it would be useless information. So net basically means, whenever you see it in front of some term, net means what's left over after subtracting out the stuff that you don't care about or don't want. In this case, they would have weighed the box before filling it with the tea bags, and then they would stuff 20 tea bags in there, and then they would weigh it again, and they would subtract out however much the box itself weighed, so that they would get this 25 gram figure. When it comes to taxes, your net taxes, or not your net taxes, your net income, actually when you look at your paycheck, you will see that you have something called a gross income. Gross income or gross pay, which is the actual amount that you were supposed to earn, and they will subtract out any tax withholding. I think I've spelt withholding wrong. Does it have two H's or just one? I'm going to go with two H's, although that kind of feels wrong. So gross income minus tax withholding equals your net income or your net pay, however it's phrased on your paycheck. Because at the end of the day, yeah, you know that you owe taxes, but you want to figure out how much you actually get to take home after the taxes are all done with. After the taxes are all done and over with, you want to figure out what is your actual net income. Of course, people who want to brag about how much money they make without being honest about how much money they take home will often report their gross salary or income in order to impress people. They don't tell you how much is left after taxes. Net income is basically income after taxes. So what about net force? How does this term apply to forces? Net force is what's left over after all forces have been accounted for. So basically, net force is the vector sum of the forces acting on an object. If I have a box and I have one person pushing on it with a force of, let's say, 30 newtons, and we'll talk about what newtons are later, and I have another person on the other side pushing on it with a force of 10 newtons, what's the net force on this box? Well, the net force would just be 20. Net force would just be 20 newtons to the right. 30 to the right minus 10 to the left, you're left with an overall force of 20 newtons. It's like you got 30 newtons in gross force minus 10 newtons in taxes, for lack of a better term. and you're left with 20 newtons overall. I know I probably ended up sounding like a broken record at some point with this, but it's really important to remember this key word, net. Because at the end of the day, it's the net force acting on an object that determines whether or not that object will experience a change in its motion state, a change in its velocity, whether it be a change in direction only or magnitude only, or both direction and magnitude. To get that change, you must have a net force. If I have, two equal forces on opposite sides of an object, okay, net force is 0, so the two forces pushing on it might as well not be there at all. If I have a 15 Newton force this way and a 15 Newton force that way, they just cancel each other out. And if this object was originally at rest, it will stay at rest. If this object was originally moving at, 3 meters per second to the right, then it will remain moving at 3 meters per second to the right. So that is Newton's first law. I need to go and put my tea box away now. Give me a minute. I probably should have made myself some tea before starting the stream. Maybe not chamomile tea because I don't want to start feeling drowsy, but orange tea would be nice. Getting vitamin C during the winter is kind of important. Anyway, so I guess we will reiterate Newton's first law, basically, to put it kind of closer to layman's terms. Whatever velocity an object has, even if that velocity is 0, that is the object being at rest, whatever velocity the object has will be constant. And the only way to change that is to have a net force act on that object. There has to be some amount of force, and it has to total to more than 0. If multiple forces are involved, you need to do some vector addition and figure out how much force overall there is before you can begin to calculate how the velocity of an object changes. And as for actually calculating the amount by which the velocity of an object would change under a net force and the direction, that will be for Newton's second law. But before we get into Newton's second law, I want to go over this term over here, inertia. What on earth is inertia? Well, inertia is basically the word that Newton came up with to describe, well, I don't know if he invented the word. Maybe that's not the best way to phrase that, because I don't honestly know if it was his word or if it already existed and he just took it and used it as a physics term. But inertia is basically the word that Newton used for this behavior, this tendency to resist change to your velocity. An object's tendency to resist change, that is what we call inertia. Inertia, an object's tendency to resist change to its motion state. To resist change to its motion state. And motion state is just a fancy way of saying velocity. So yeah, Newton called this behavior inertia, and a lot of people misuse this term, they don't misuse this term, they misuse another term when they actually mean inertia. What they will say is that, for example, a big truck, an 18-wheeler truck, has a hard time stopping and turning on a dime because it has a lot of momentum. But that's not true. We will learn about momentum later. Momentum is a different idea. Momentum is a different idea. For now, all I will tell you is that it's equal to an object's mass times its velocity. And so, if you explain a truck being hard to slow down by it having a lot of momentum, that's not true, because when that same truck is at rest, zero velocity, it has no momentum. And yet, despite having no momentum, it's not exactly easy to get it started to move. It's not exactly easy to push it in such a way that it actually starts moving. It requires a lot of force to get it to start moving. So if momentum was the actual explanation here, then it doesn't work for the case where the truck starts off not moving. The term that we're really looking for is inertia. An object's inertia is what carries it through if it's already moving. An object's inertia is what causes you, we'll see this later when we get to the circular motion chapter, but let's say I'm looking from above, and let's say from above, like from my helicopter perspective in the sky, I look down and I see this car, and the car turns this way. And you feel like the person inside the car feels like they are being flung outward. Why is that? Well, that's because the person in the car is trying to continue moving in a straight line. And the car itself turns. And so the person in the car finds themselves being pulled here to the side of the car. So from their perspective, it looks like they're being pushed outward, but they're not being pushed outward. They're just staying on their initial path. Their inertia is trying to prevent them from turning, while the car has enough force on it due to like friction from the road and all that stuff, that the car successfully turns before the person does. The person does eventually turn because, worst case scenario, they bump into the walls of the car, and then that produces a force that pushes them back onto the same path as the car. We will elaborate on that more when we get to the circular motion chapter. But yeah, that's just inertia at work over there. If you're walking in a sort of downhill direction, that's inertia. Well, it's inertia and it's also acceleration from gravity. So yeah, inertia is an object's tendency to resist change to its motion state, and objects exhibit more of this behavior the more mass they have. The more mass an object has, the more inertia it will have. And we will dig into the role of mass in a little bit once we talk about Newton's second law, but before that, I think we should do a quick review of calculating vector sums. So let me switch to this screen. Okay, and here you see some notation. So get used to seeing this symbol over here. This is the capital sigma. It means the sum or the total of and then whatever comes after it. So sum of forces equals the vector sum of all of the forces, also known as net force. Let's see. So let's go ahead and figure out these vector sums. First one is pretty easy. You've got 25 to the right and 10 to the left. That should be a total of 15 to the right. You've got 12 to the right and 16 to the right. That should be a total of 28 to the right. Over here with C, we've got 6 up and 8 to the right. That would be, if we do Pythagorean theorem, 6 squared plus 8 squared is 36 plus 64 is 100. And if we take the square root, that would have to be 10 newtons up and to the right. So essentially what you could do, and you could actually experiment with this at home if you were precise enough, you could actually push this box with an 8 Newton force to the right and a 6 Newton force upward, and then compare that to just pushing that same box with a 10 Newton force at the appropriate angle. And you would find that in both cases, the movement would happen in the exact same way. You'd probably need like machinery or something to make sure that you were actually measuring the force accurately, to make sure you were getting the exact numbers you were supposed to. But I think you can imagine why this would work, even without having the necessary equipment to do the experiment. Okay, D and E. I'll just do D. So with D, you would do 35 cosine of 34 degrees to get the part of the red vector that points to the right. You would do 35 sine of 34 degrees to get the part of it that points up. Then for the blue vector, you would do 20 cosine 45 gives you the leftward component, and 20 newtons times sine of 45 degrees gives you the downward component. So you would have, I would imagine, more downward than upward force. So I think you would do just down minus up if the downward force is actually greater. And then I think the rightward component of the red vector is greater than the leftward component of the blue one. So right minus left, you'd be left with some vertical vector and some horizontal vector, and then from there it's just like part C. You would do Pythagorean theorem and use inverse tangent to calculate the angle, and there you go. Part E isn't going to be that much different. You just have 3 forces to deal with instead of 2, but same idea. Just decompose your vectors using your sines and cosines, get all the horizontal parts and add them up or subtract as the case may turn out to be. And same thing for all of your verticals. And once you have your total vertical and your total horizontal, do Pythagorean theorem on those 2 totals to get your final 2-dimensional total. And yeah, there is more to this worksheet, but we haven't covered that yet. So let's actually talk about that. Let's move back to our camera. And let's see what's next. Flip over to here. Let me get a sip of water, for it's starting to feel a bit dry. Okay. And let's go ahead and talk about Newton's second law. Newton's second law. This is nicknamed the law of acceleration. Most people don't remember the nicknames, but I think they are important. Newton's second law, the law of acceleration. This one is actually just a mathematical formula, but we can write it in words too. Basically, it will say that the acceleration of an object, is directly proportional, whoops, that's not how you spell directly, directly proportional to the net force acting on it, and inversely proportional, proportional to its mass. So mathematically, it would look like this. The acceleration of an object is directly proportional to the net force acting on an object. So the greater the net force, the greater the acceleration. And inversely proportional to its mass. So divide by the mass, because the greater the mass, the lower the acceleration. This can be rearranged into something that I'm sure some of you have just seen through just sheer internet exposure. Net force equals ma. Or some people write it as just F equals ma, which I guess is fine, but it kind of robs you of the reminder that you have to actually calculate the total of the forces. This I don't really like, unless you modify it by using the word net. Then I'm okay with it. So if you're not confident about your ability to write the capital sigma symbol, I mean, you're going to need to learn it eventually, because most students doing physics are probably taking calculus or going to take calculus, and once you get to calculus 2, whether you do it early as Calc BC in high school or you do it later in college, you're going to be doing all sorts of summations towards the end of a Calc 2 course, and yeah, you're going to need to learn how to draw this symbol. I don't think it's too bad. It's a sideways M, and then with hooks. That's really all it is. Just practice it a couple times and you will get the hang of it. But yeah, this is probably the pop culture version that some of you have been exposed to before you ever took physics. You probably have seen it in, like, I don't know, random physics videos or other videos that bring it up whenever it becomes relevant. And yeah, there it is, Newton's second law. So the greater the net force, the greater the acceleration, the greater the mass, the lower the acceleration. So if we go back to what I had over here, we had, for example, for part A, we had 25 minus 10, net force is 15 newtons, and then you would say that that net force of 15 newtons is equal to 10 kilograms times the acceleration that this box would end up having. So if I just divide both sides by the 10 kilograms, 15 over 10, 1.5, this object is going to have an acceleration of 1.5 meters per second squared to the right. Does that mean it moves to the right? Well, that depends on which way it was moving before these forces got applied to it. If it wasn't moving at all, then yeah, it'll move to the right. But if it was, say, moving to the left already, then an acceleration to the right will slow it down first and then start moving it to the right. And if it was moving at some sort of angle, God help you, because now you have to actually break down your vector components and figure out what on earth is happening. It's probably going to be some sort of curved path like we saw in projectile motion. Okay, part B, you've got a greater magnitude of net force. 12 plus 16 is 28 as opposed to the 15 in part A, so greater force and less mass, 8 kilograms versus 10. So I expect this to have much more acceleration compared to the box in part A. 12 plus 16 was 28 equals 8 kilograms times acceleration. So 28 over 8, what is that? Well, 24 over 8 would be 3. So 3.5, right? 3.5 meters per second squared compared to the 1.5 that we got for the first object. And yeah, that's really all there is to it. Once you calculate the total force acting on an object, you can then just divide by that object's mass to figure out its acceleration. Or sometimes you'll actually know the net force and the acceleration and have to calculate the mass, or sometimes you'll know the mass and the acceleration and you'll have to calculate what the net force is. This equation can be used as long as you know any two of these three things: net force, mass, or acceleration. Okay, there was something else I wanted to say here. Oh, yes. So what on earth is a Newton? What on earth is a Newton? This equation tells us net force is going to be in units of force. If net force is equal to mass times acceleration, then we can say that the units of force are going to be equal to units of mass, which for our purposes the standard we will go with is the kilogram, times units of acceleration, which is going to be meters per second squared, is the standard that we go for. If the mass is not in kilograms, if you're given mass in grams, you're probably going to have to convert it to kilograms in most situations. And same idea for acceleration. If it's not in meters per second squared, if it's in like miles per hour squared or whatever, you're going to have to convert that, most likely. So that gives us a Newton. 1 Newton is the name that we give to this unit of kilogram meters per second squared. If you multiply kilograms by meters per second squared, you get a kilogram meter per second squared, which is also a Newton. Make sure you remember this. Make sure you remember that a Newton is a kilogram meter per second squared. Am I telling you to memorize this? No, I'm not telling you to memorize this. I do want you to memorize this. I do want you to memorize net force equals ma. And by memorize, what I really mean is understand that, well, I guess I would actually want you to remember it this way. Understand the idea that acceleration increases with more net force and decreases with more mass, and then from there you can always just kind of quickly rederive this relationship between force, mass, and acceleration, and then rearrange it to this. And once you have this, you can just do what I just did over here to get back that a Newton is a kilogram meter per second squared. On the AP exam, they will ask you questions about units like this. They'll ask you something like, oh, I don't know, you'll have an equation. Well, okay, I'll show you this one early, but we're going to quickly forget about it until we get to the circular motion and gravitation chapter. So on a more universal level, Newton's law of universal gravitation tells you that the force of gravity that two objects exert on each other is equal to some constant, capital G, times the mass of one of the objects times the mass of the other object divided by the distance between them squared. And you will find on the AP exam questions like, which of the following, it'll usually be on multiple choice, which of the following units are the correct units for the constant G? And then you'll have to go, oh, well, force is going to be in newtons equals whatever the units of G are supposed to be. And then the first mass is going to be in kilograms, and the second mass is going to be in kilograms, and then the distance between them squared is going to be in meters squared. And then you'll look at the answer choices, and none of the answer choices have newtons in them. And that's when you'll panic and go, oh no, but those who prepared well enough ahead of time will realize, oh, I can just rewrite the newtons as kilogram meters per second squared. And again, if you don't remember this, just use any of your force equations to get newtons equals and then just sub in the units of all the other variables in that equation. And once you do that, you go, let's see, newtons, so kilogram meters per second squared equals whatever the units of G are, times, I guess that's going to be kilograms squared over meters squared, and then you multiply the meters squared and divide by kilograms squared, and you get, well, kilograms over kilograms squared, and then meters squared times the meters I already had becomes meters cubed, and then you still have the seconds squared. That was a bad looking 2 over there. Equals whatever the units of G are supposed to be, and then you can cancel 1 power of kilograms from the top and bottom, and you get cubic meters per kilogram second squared. And then you find that among your answer choices and you circle it, or, well, I guess bubble it in for your Scantron, or actually just click it, because this year they're doing the multiple choice portion online, if I remember correctly. Or is it the multiple choice and the free response? I need to double check the list, because I know they made some of them completely online, while some of them are only half online, and I keep forgetting which ones are which, but I'll have to read up on that and double check. But you get my point. You get my point. Get in the habit of practicing this sort of unit derivation thing. Get in the habit of practicing this. Later on in the next chapter, we're going to come across the units of joules, and those are going to be, we'll represent them with a capital J for joules, but they're also going to be able to be converted to just some combination of kilograms and meters and seconds and all that. Almost everything you see in AP Physics, or actually maybe everything, at least in Physics 1 and Physics C Mechanics, will boil down to some combination of kilograms, meters, and or seconds. So yeah, there's my mini rant on rewriting your simplified units back in terms of, what would I call these? I guess base units. I'm blanking on the official term, standard units. Okay, so that's Newton's second law. We have discussed it. So where do I want to go from here? Let me double check my list and make sure I'm not forgetting anything. G-forces and why they're not forces. Okay, I'll talk about this briefly. So suppose you do Newton's second law. You figure out what forces are acting on an object. You calculate the vector sum. You divide by the mass. You get the acceleration. And then the question asks you, what are the G-forces acting on this object? Well, G-force is not a force. G-forces is a misleading term. G-forces is not a force. Basically, what they're asking is how many multiples of G, how many multiples of G is the acceleration in question. Because, we as humans are still somewhat egocentric in our study of the laws of the universe. We still like to try and think of things relative to what's familiar to us. So we like to compare to just the acceleration due to gravity that we experience every day. If I drive a Formula One race car, if I launch a rocket, how much acceleration do I experience when in those vehicles? Would a rocket be considered a vehicle? I'll have to look that up later. But you get what I mean. So, yeah, it's really just take whatever acceleration you've calculated, G-forces, equals the acceleration divided by G. And that's really it. If I have an acceleration, I calculate it to be, 98 meters per second squared, then divided by 9.8, that comes out to exactly 10. So the object in question would be experiencing a G-force of 10G. It's just got an acceleration of 10 times G. That's all it is. So I would have preferred calling them G accelerations instead of G forces, but I didn't really have the privilege of being there whenever they coined this term. So it is what it is. If you come across that, you'll often, well, not very often, but maybe like 2% of the time, you might see a question that will ask you, compare the acceleration you obtained to the acceleration due to gravity on the surface of the Earth. And what they want you to do is just calculate the ratio and tell us how many times the thing you're comparing to is the thing that you calculated, if that makes any sense. And they'll ask all sorts of compare questions. It's not always just going to be asking for G-forces. They'll ask things like, they'll ask you to calculate the force it takes for, say, a rope to snap, and then they'll say, compare this to the force it takes to break bones, estimated at however many newtons. And that just means divide by the thing they're asking you to compare to and answer how many multiples did you get. That's all it is. It's just calculating a ratio. So that's G-forces. Anything else? I think we are ready to talk about some commonly encountered forces and talk about free body diagrams, or force body diagrams, however you want to call them. I know the official term is free body diagrams, but force body diagram works too because it's a diagram where you draw the body, the object, and you also draw forces. In fact, you were looking at force body diagrams earlier. So let's go ahead and switch screens. Okay, so this is an exercise that I do have on the course plan. Again, if you're new here, course plan is always linked in the description of these videos and streams. So it should be under the force diagram practice material. So we've got ourselves first off a summary of the 7 main forces that you will see in Physics 1 and Physics C. There are a couple that I have left out because they are not often encountered, but we'll deal with them when we get to them. So in order to do force problems successfully, I find that it's more helpful to first practice identifying which forces are present and make sure you get your force diagram right. So this exercise, this whole worksheet, no actual calculation is needed here. The only thing that you need to do here is identify which forces are present and what are their directions. And that's it. Just get the diagram right. We will worry about the numbers in future exercises. So that'll be coming up, but first let's discuss all of these different types of forces. So the first type of force is normal force. It is called normal force not because it's normal in the sense that it's ordinary, but because of the mathematical definition of the word normal. In math, in geometry specifically, the word normal means perpendicular. And it even says right there, always points in a direction. Actually, let me zoom this in a little bit. Or maybe a lot. Always points in a direction that is normal. In other words, perpendicular to the contact surface between two objects and always pushes an object away. It always exists when two objects touch each other. So it always pushes. It does not pull. Very, very important. It always pushes away. It never pulls towards. And it always exists when two objects touch each other. So if one object is touching another, there is a normal force between them. And the other object doesn't have to be an object in the literal sense. Even the floor or the walls can be considered a second object that your first object touches. If two things are in physical contact with each other, there's going to be some sort of normal force between them. Except in maybe some sort of edge case where they're technically in contact but just barely touching each other. But we'll talk about those cases later. Okay. Next up, we have the force of gravity, also known as weight, and this is why the colloquial definition of weight is not very helpful for studying physics. Weight is a force, not a mass. Always exists on Earth and always points straight down toward Earth's core. Works in a similar way on the moon or on other planets as well. So you don't just have weight on Earth, you have weights on the moon, on Mars, on Venus, wherever. And it's always going to be straight down towards the, maybe core isn't the right word to use, but towards the center of mass of whatever is exerting that gravitational force on the object. For our purposes, at least for now, we're just going to be dealing with flat Earth physics. We will deal with the other version of gravity in a later chapter. So for now, straight down. If an object exists on Earth, which is going to be our default assumption unless the problem tells us otherwise, we always draw a gravitational force vector straight down. Okay, next up, static friction, which I guess I should have gone over the notation that I use for all of these forces. So I will usually just use a capital F and then a subscript to tell you what type of force it is. But I've also listed some commonly used alternatives, like a lowercase w for weight. Capital W is taken for something that we will learn about in the next chapter, so we will see why lowercase w is preferred if you want to use W for weight. Anyway, static friction. So I like to represent it like this: force and then a lowercase f, comma s. The lowercase f stands for friction, and then the s stands for static. The force of static friction always points parallel to the surface of contact between two objects. Only exists when an object does not slide against another rough object that it is touching, such as a box not sliding along the ground or a box not slipping off the top of a moving car. We will talk about the importance of that later. I'm very particular about the wording there. It's not about motion, it's about relative motion. We'll get back to that whenever we have a stream more focused on the topic of friction. Always points in a direction opposite to the direction of attempted motion. I would modify this a little bit and say opposite to the direction of attempted relative motion. Again, don't worry about that. We'll talk about it later when we have a more friction-focused lecture. Okay, number 4, kinetic friction, the other type of friction. This I represent as force and then lowercase f, comma, lowercase k for kinetic friction. Or you can just go with a lowercase f sub k. That also works. Always points parallel to the surface of contact between two objects, just like the static friction. Only exists if an object is sliding against another rough object that it's touching. Always points in a direction opposite to the object's direction of motion. And again, I would add the word relative in there. Opposite to the object's direction of relative motion, but we will talk about that in the future. Spring force always points opposite to the direction that the spring or rubber band or whatever was stretched or compressed. Only exists when an object is touching a spring or some elastic material, and I would also add that that elastic material would have to be stretched or compressed from its default length. Okay, next up is tension. A lot of times people will represent it with a capital T, but we will use capital T for something else in the future, so I would recommend getting in the habit of writing it like this as F sub T. Only exists when an object or person is attached to something that is pulled taut, such as a rope, string, wire, cable, chain, etc. Always pulls the object inward, towards the rope, string, etc. So basically the opposite of normal force. Normal force always pushes away. Tension always pulls toward. So you should not be making mistakes when it comes to the direction for tension or normal force. And And then number 7, this isn't really a force. It's just, again, humans being egocentric. Applied force, sometimes called FA or FAPP for applied, just an abbreviation. It always points in the direction that the person or machine pushes or pulls another object, only exists if the problem states that an object is being pushed or pulled by a person or machine. So basically, applied force will usually be either a tension force or a normal force, or sometimes even a friction force, especially a static friction force. So applied force isn't really like a real class of force. It's just what we call the normal tension or friction force that we are using whenever it's being used to move an object intentionally. That's what makes it an applied force. It's that we are intentionally applying it to cause an object to move in a certain way. But otherwise, applied force isn't real. It's always some other type of force. Though it is still a useful concept, because if you have, multiple forces of the same kind, like more than one normal force acting on an object, being able to name one of them the applied force and the other one the normal force might just make it easier to keep track of things instead of labeling them normal force 1 and normal force 2. So it has its uses. Okay, was there anything else I wanted to add here before looking at the exercises? Let me think. I guess I want to really quickly just draw. So for normal force, we're going to see situations. So we're going to see, for example, a situation, I think our first one actually is going to be a box lying on the ground, and it said that normal force is always in a direction perpendicular to the contact surface between two objects. What does that mean? The contact surface between two objects. Basically what that means is, where do the two objects overlap each other? Where is the touching happening? So in the case of a box on the floor, that would be right here. Right there. That's your contact surface, as I would call it. So normal force is in a direction that's perpendicular to this, and it always pushes away. So the ground is going to push the box away. Which way would that be? That would be straight up. So that's where we would draw the normal force. We would draw it pointing straight up. As for where you actually draw it, for now, we don't care. Once we get to the rotational dynamics chapter, we're going to have to be more careful about it. But for now, you can draw your forces anywhere on the object, and it'll be fine. But once we start talking about the rotational effect of those forces, we're going to have to be very careful with where we are drawing them, because where a force is applied matters. And in case that isn't making much sense to you, then without telling you too much, because I want to save it for later, try opening a door by pushing or pulling on it from the doorknob versus from towards the middle of the door versus closer to the hinges. And you'll see that if you use the same amount of force at different positions, you're going to get different results. That's all I will say about that for now. But yeah, we can get away with not being too careful with where we draw our forces for the time being. Now, another case I'll just wait until we come across all of the different situations in this PDF. Yeah, I don't want to give away the game too early. Let me see. What else? What else did I want to talk about? The friction forces are parallel to the contact surface between two objects. So if we had reason to believe that this box over here was experiencing friction, it would have to be this way or this way. Those are your only two options. Friction has to be parallel to the surface of contact between the two objects. The two objects here being, of course, the block and the floor. Let's see. Spring force always points opposite to the direction that the spring or rubber band was stretched or compressed. So here's a spring, and it doesn't have a lot of tolerance for compression, but if I push it, it pushes back on me. If I pull it, it pulls back. So it's kind of like a 2-in-1. It kind of does what tension does, but also can do what normal force does. If I push on it, it kind of does what normal force does and pushes back. If I pull on it, it kind of does what a rope would do and pulls back. And the farther you stretch it, or the farther you compress it, the stronger that force will be. Anything else? I think that is everything for now. Let's go ahead and have a look at these questions, and I guess I'll be toggling back and forth between the PDF and the camera. Okay, so it says for each diagram below, indicate which types of force are present and draw those forces on the diagram, showing their directions. You don't have to show the forces on the people, walls, or ground. Only show the forces that have an effect on the block. You also don't have to calculate or show any magnitudes or angles. So, situation 1. A block remains at rest on the ground as shown. So you've got a non-moving block. This one should be rather simple. It's basically what I drew, except it wasn't complete. You would have a normal force on this block pointing upward, and you would have, of course, a gravitational force, because unless we are told otherwise, we should assume this is happening on Earth. So force of gravity is probably going to be the first thing you put on your force diagrams every time you do one. Number 2. Now, someone tries to push the block to the right, but it still doesn't move. Now someone tries to push the block to the right, but it still doesn't move. And over here I said these tick marks mean that the surface is rough and creates friction. If you don't see them, then it probably means that the surface is smooth and there's no friction, but you still need to read the problem carefully to make sure. So, the AP exam does use these tick marks, but sometimes they just use it for shading and clarifying their diagrams and not necessarily as an indication of friction. I have seen AP exam problems where they will draw the tick marks and then the problem will say the surface is smooth. So my drawings will use the tick marks to mean that there is friction, but that doesn't mean everybody else's drawings will use the same meaning. So be careful about that. Anyway, someone tries to push the block to the right, but it still doesn't move. So how does this differ from the diagram we had for number 1? So I'm going to switch back to the camera, and let's have a look at that one. Oh goodness. There we go. That's better. Okay, so we've got a person pushing the block. Well, that means that there's some sort of intentional application of force. So this is what I would call an applied force. Of course, we still have normal force because this object is in contact with the ground, and we've got a force of gravity because we can assume that this object is on Earth and gravity must be pulling it down. And then they said there was friction. So in this case, the object isn't moving relative to the ground and in fact isn't moving at all. So what kind of friction would that be? Static friction or kinetic friction? Well, if we scroll back up here to the quick definitions that I gave, static friction only exists when an object does not slide against another rough object that it's touching, such as a box not sliding along the ground. So yes, we are talking about static friction here. Kinetic friction would require some sort of actual movement to be happening. And again, we'll talk about these two types of friction and the differences between them in more detail in a later lesson. But for now, just the fact that the box does not move tells us that this is a static friction force, and its direction for static friction is opposite to the direction of attempted motion. So how to figure out the direction of attempted motion? Basically, you draw your force diagram with everything except for the friction. You save the friction for last. And then you ask yourself, with the forces I have currently drawn, if there was no friction, which way would this object move, assuming it started from rest? Well, it looks like you've got a force upward and a force downward that are going to kill each other off, and it looks like this object is going to move to the right in the absence of friction. So the static friction is going to apply to the left. Force, friction static, is going to be to the left. It's going to try and resist the attempted motion. And there you go, that diagram is now complete. Now, I might as well talk about this while we're here. So, force applied. I said earlier that the applied force is actually going to be one of the other types of force. So in this case, what type of force would it actually be if a person is physically pushing on a box with their hands? What are they doing? What kind of force is that? Well, that's a normal force. They're going to put their hands in a direction that's perpendicular to the ground. Hold on. No, I don't want to use that phrasing. That's too confusing. They will probably just put their hands like this, right? Just flat against the surface of the box. And the normal force, because the hand and the box would be touching at that point, the direction perpendicular to that contact surface between the two would have to be perpendicular to the hand, or in other words, away from the hand. So the box is being pushed perpendicularly away from the hand, that is, to the right, if you assume the hand is, oriented vertically when touching the box. So yeah, this applied force is actually just a normal force that is being intentionally applied by a human. If the person was pulling the box, they would actually be using friction force there. They'd be using the friction between their fingers and the side surfaces of the box. And of course, if they had like a rope attached to the box and they were dragging it, then their applied force would, in truth, be a tension force. So there's that. The topic of applied force, I think I've now sufficiently explained why it's not a real force, and it's always just one of the other force types, just being given a more, I guess, intuitive name for the purposes of the problem. Anyway, back to diagramming. Diagram 3, it says here, the block is moving to the left and the person is trying to stop it. So here you have an already moving object. What forces exist on it? Well, it's not going to be too different from the diagram we already have. So I guess we will draw a diagram 3. And I should probably number these in case people want to, go through them later. So diagram 3, you have, the person is going to be pushing to the right, so force applied is still there compared to the previous scenario. Normal force between the block and the ground should still be there. The earth didn't disappear from underneath the box, so the force of gravity should still be there. And the object was moving to the left. If an object is moving to the left, first of all, because it's moving relative to the ground, it can't encounter static friction, but we did see those tick marks in the diagram. We did see those tick marks. They're still there in the diagram, and I should probably include them here. So we know friction is involved, and it can't be static friction, so that leaves us with kinetic friction. Kinetic friction is always opposite to the direction of the object's actual motion relative to the surface causing the friction. So if this object is moving to the left, then the kinetic friction has to be to the right. So basically what this means is that you've got two forces to the right pushing on an object that's moving to the left. Your net force is going to be to the right, which means your acceleration is going to be to the right, which means this object is being slowed down, which makes perfect sense. That's literally what it said in the problem. It said the block is moving to the left and the person is trying to stop it. Even without the person's help, the kinetic friction would have eventually slowed it down. Okay, number 4, this diagram shows a person who has successfully caused the block to move to the right. So basically the same as scenario 3, the only difference is that now the velocity is to the right. So basically what happened is it was moving to the left, they slowed it down, they brought it to the stop, they kept pushing, and now it's moving to the right. So now what changes is the direction of the kinetic friction. Now what changes is the direction of the kinetic friction, so everything else stays the same. Diagram 4. Force of gravity is still straight down, normal force is still straight up. The person is still applying a force to the right. That's what the problem told us anyway. And then because the object's velocity is to the right, the kinetic friction must then be to the left. The kinetic friction is making this person's job harder. This person is now being opposed, whereas in the previous scenario, the friction was helping them. And there we go, that's diagram number 4. Okay, let's see what we have next. Now the person pushes the block against a spring, which is attached to a wall. Okay, so the spring has been pushed, which means it's going to push back. And compared to diagram 4, the only thing we would add is a spring force. Since the spring was compressed to the right, it would have to push back to the left. It would have to push back to the left. So I guess we will draw one over here. Number 5. I'm just going to draw the block. I'm not going to draw all the other stuff because then it'll be hard to read our diagram. The applied force is still to the right. The object is moving to the right, so the kinetic friction must still be to the left as it was in the previous scenario. So there's force of friction, kinetic. Normal force, still up. The floor hasn't tilted at an angle or anything like that, so normal force should still be just perpendicular in a way, and force of gravity straight down. And since the spring is compressed to the right, it will push back to the left, so I guess I will draw it over here, even though it's not technically on the box. I probably should have made the box a little bit taller, but FS, force spring. And there we go. That's diagram 5. Okay, diagram 6. The person leaves the block after compressing the spring, but the block doesn't move. Okay, block not moving. I need to remember to just not click these pens since I'm still using them. That's a habit that's gonna take a while to develop. Anyway, so they leave the block after compressing the spring, but the block doesn't move. Okay, so we still have a rough surface as indicated by the tick marks. And also, even if I didn't have the tick marks, there would have to be something preventing the motion of this block. So, force of gravity and normal force, of course. And then we've got, so the spring was compressed to the right, which means there must be a spring force pushing back to the left. There is no longer an applied force because there is no person involved anymore. And I don't see any ropes yet, so we haven't encountered any situation where tension would apply. That just leaves the friction force, and since the object isn't moving, we know we're talking about static friction. Static friction is opposite to the direction of attempted motion. Where is the direction of attempted motion? Which way would this object move if that static friction was not present? We currently don't have the static friction on our diagram, so it's easy to see that this object would move to the left in the absence of friction, which means our static friction must be to the right. Force of friction, static. I would have drawn it down here like I did in previous diagrams, but like I said, we're not going to worry too much about where we draw our force vectors for now. That'll become important in the rotational dynamics chapter. I just figured since I've got more room to the left, that's where I would draw it. And also, I forgot to number it. This was diagram number 6. Okay. Oh, why did... There, that's better. Okay. Number 7. In a scenario similar to the previous case, someone pushes a block against a spring and lets it go, but this time the surface is smooth and the block is about to move. So basically, same diagram as before. Oh, and I forgot to show you that on screen. Hold on. There we go. In a scenario similar to the previous case, someone pushes a block against a spring and lets it go, but this time the surface is smooth and the block is about to move. Well, even without knowing physics, we know what's going to happen. That object is about to slide to the left. Okay, so no more tick marks, no more friction. It's a smooth surface. There's still going to be a normal force upward and a gravitational force downward. And since the spring was compressed to the right, it will push back to the left, so the spring force is to the left, and that's it. Compared to the previous situation, all we really did was we removed the friction. All right, diagram number 8. A block has just been placed on a smooth ramp and is about to slide down. Gotta remember to keep switching back. Okay. So we have a block on a smooth ramp. What forces are acting on this thing? Well, it's presumably on planet Earth, so force of gravity straight down. It is touching a surface, so there must be a normal force perpendicular to and away from that surface, which would be in this direction. Perpendicular to the surface and away from the surface. And that's it. There's no roughness to this surface, so neither type of friction is involved. And I see no ropes or springs, so no tension and no spring force, and I don't see any people or machines intentionally trying to push or pull this object, so no applied force. That's it. We're done. Okay, next scenario. In a scenario similar to the previous one, a block is placed on a ramp but never slides down. Okay, so the diagram for scenario number 9 should be the same as scenario 8, except for the presence of friction. Except for the presence of friction. So let's go ahead and see. I guess I drew that ramp a little too steep compared to the previous one. Not that it's really going to matter here. And then tick marks. And you've still got force of gravity straight down. And normal force perpendicular to the ramp and away from the ramp. And this object is not moving, which means the type of friction we are working with here is static friction, which is going to oppose the direction of attempted motion. Which way would this object have moved if not for friction? In other words, if we look at scenario 8, which way was this object going to move, just depending on your common sense? If you placed a block on a smooth ramp, would it slide down or would it slide up? Of course it would slide down. If you want to think about it in terms of just trying to come up with the sum of these vectors, if you drew them tail to tip, if you drew normal force like this and then gravitational force like this, then you could find that the resultant of those two forces is going to be something like that, right? Connect the exposed tail to the last exposed tip, and you see that the sum of the forces is in this downward diagonal direction. So we know that this object is going to move diagonally downward in the absence of friction, which means since it's not moving, the static friction must be acting up the ramp. Force of friction static up the ramp. I hope that's actually going to end up readable in the final recording. I hope. But we'll just have to wait and see. Okay, scenario number 10. Now someone attempts to push the block up the ramp, but still can't get it to move. So when I originally wrote this problem, I had intended for it to only have one solution, but when reviewing it with some students for the first time, I realized that actually it has two possible answers. So we're going to need to go over that, and I think I'm going to want to start a new sheet for it. Yeah, the backside of that sheet is already filled, so yeah, let's start a new sheet for this. And maybe we should switch up our colors, since purple and green are kind of getting, I don't know, what's the word? Boring? Boring isn't the exact word, but I guess overused. That's not the right word either, but it's what I'll have to go with. Okay, scenario 10. So we've got rough surface and a block, and we've got force of gravity straight down, normal force perpendicular and away. The person is trying to push in a direction up the ramp, so that would be the direction of the applied force. I don't see any springs or ropes or cables or anything like that, so tension force and spring force can be ruled out. Now we're left with friction force, two types, kinetic and static. Well, this block is not moving relative to that ramp, so static friction it is. Static friction is always opposite to the direction of attempted motion. So the question is, which way will this object move? In the absence of friction, which way would it have moved? There's actually two possible answers for this, because we already showed that when you do the vector sum of normal force and gravitational force, you end up with their total being something that's pointing down the ramp. But then depending on how big this applied force is, if this applied force is too small, then that downward sum of the normal force and the gravity would still be enough to make the box go down. So if this person pushing up the ramp is too weak, then in the absence of friction, the box would have been sliding down anyway and dragging down the person with it. But if the applied force is stronger, then they will overcome the combination of normal force and gravity, and the object would have been sliding up the ramp. So technically you have two possibilities for your static friction here. It can be up the ramp or down the ramp. It will be down the ramp if this applied force is larger, and it will be up the ramp if this applied force is too weak. The static friction will apply up the ramp to make up the difference in order to prevent the block from sliding down. So you actually have two different possibilities for the force of static friction here. And now this is not a correct diagram if you draw both on the same diagram, but in order to save ink and paper, I'm just gonna leave it like this. But technically, what you would have to do if it were on a test is you would have to draw two diagrams, one with the static friction up the ramp and then another one with the static friction down the ramp. And you would have to explain, you would have to justify in words that this diagram is when the applied force is too high, this diagram is when the applied force is too low, and yeah. So number 10 actually has two possibilities you need to consider. All right, next one. Number 11, after setting up a rope with a pulley and getting some help from a friend, the person from before manages to finally get the block moving up the ramp. Finally, we have a problem that involves rope. Okay, and I still see the tick marks, so friction is still involved, but the object is moving, so it's not static friction anymore. It has to be kinetic friction. Okay, force of friction kinetic is going to be in our diagram. And the great thing with kinetic friction is that it's usually really easy to tell which direction it's going to be because you know the velocity, so you just have to go opposite to that. Okay, block. And forces are normal force, force of gravity straight down, applied force up the ramp. In case I didn't mention it before, the direction of the applied force is just supposed to be given in the problem, unless it's a problem where it's specifically asking you how much force and in what direction must you apply in order to get whatever situation the problem is asking you to fulfill. But outside of that, you will typically just be told which direction the applied force is, or they might just draw the diagram for you in the problem itself. So the direction of applied force is just wherever the problem says its direction is. Anyway, oh, and I forgot to draw my tick marks. The velocity of this thing was up the ramp, so the force of kinetic friction would have to be down the ramp, so that's force of friction kinetic. And the new thing is the rope. So we've got a rope on the upper side of the block, and ropes pull, they do not push. Ropes pull, so it's going to be parallel to the rope and towards the rope. It's going to be like this. That's going to be the direction of our force of tension, F sub T. All right. Next scenario. Scenario 12. The two people from before try to move a heavier block but fail as it slides down the ramp. Okay, so the only thing that changes between this and the previous scenario is the direction of motion, but everything else should still be the same as far as our diagram is concerned. So scenario 12 oh, and the block. Gotta draw that before I switch colors here. So The only thing that changes is the direction of the velocity. The rope is still on the upper side of the block, so the force of tension should still be pulling it in a direction up the ramp. The person on the bottom side of the block is still trying to push it upward, so force applied should still be in that direction. Normal force shouldn't have changed. Normal force, whoops. Is that? Yeah, okay, that's on the page. Force of gravity should be straight down, force of gravity. And the force of kinetic friction, if the object is sliding down, then the kinetic friction would have to be trying to drag it back up, or at the very least, force, friction, kinetic. I did not make enough space for this, did I? Nope. That's not even readable, is it? And come to think of it, force of tension isn't readable either. Okay, there we go. Force of tension, and then this, I'll just write it off to the side here. Force, friction, kinetic, and then I'll just do a squiggly arrow pointing to it. I don't know, I feel like that diagram is still not very readable, but at least you understand what I'm trying to draw, and hopefully you will do a better job than me with your own drawing of the diagram, if you have been following along. Okay, scenario 13. Here's a smooth ramp with a block placed onto it, which is kept in place by a compressed spring. Okay. So scenario 13, compressed spring. So we've got a block right here, smooth ramp, there should be force of gravity straight down, and normal force perpendicular to the ramp, and no applied forces because the person has been removed, no friction forces to worry about, there's no rope so the tension force is gone. But there's a spring now, and the spring has been compressed in a direction down the ramp, so it will try to push back in a direction up the ramp. So the spring force must be this way, which makes sense because without the spring force, normal force plus gravity would have a total force that's down the ramp, and the object would be sliding down. So something has to be pushing it back up the ramp to prevent that from happening. All right, getting closer to the end. Number 14, how many do we have? 18? No, 17. Yeah, we're getting there. 4 more to go. 14, a block is left hanging from the ceiling by a rope. Scenario 14, a block is left hanging from the ceiling by a rope. Okay, what forces are acting on this? Well, we assume this is still on Earth, so force of gravity straight down, and the rope is gonna be pulling up. The rope would have to pull up, so force of tension upward. This block is not in contact with any surfaces, so no normal force for once. There are no springs, and if you're not in contact with a surface, then you can't have friction either, so that rules out everything, and there are no people or machines pushing or pulling on it, so no applied force to consider either. All right, that's scenario 14. Scenario 15. Now someone pushes the block to the left while it's still hanging. It doesn't touch the wall. Okay, so now the object looks like this. So force of gravity acts downward on it. Force of tension is towards and parallel to the rope. And the person pushing it would have to be pushing it to the left. So there's your force applied, and that's it. Nothing else has changed from the previous scenario. So that is scenario 15. Scenario 16, second to last. The person continues to push the block until it's pressed against the wall. Okay. Well, the wall is a surface that this object has come into contact with. So now we have force of gravity downward, force of tension along the rope and towards the rope, force applied to the left, and since this object is now in contact with the wall, there has to be a force perpendicular to the wall and away from the wall. That would have to be to the right. So normal force to the right. I guess I could draw it here or I could draw it here. I'll draw it here. Normal force of the wall perpendicular to the wall and away from the wall, pushing back on the block. And finally, scenario 17, the block gets detached from the rope and gets hooked onto a spring that is connected to the ceiling. Scenario 17. The block gets connected to a spring. Common sense would suggest that the spring would stretch in this scenario. So it got stretched downward. You could imagine if you remove the block, the spring would just, pull back up to whatever its original length was. So here you've got force of gravity straight down. No applied forces because the person is gone. No tension forces because the rope is gone. No normal forces or friction forces because there's no contact with the surface. All that's left is the spring force, which would have to be up. The spring got pulled down, so it's going to pull back up on the object. And there we go. So again, I think this exercise is important because it just gets you to focus on identifying what forces are present in the scenario that I'm looking at. And of course, there are more complicated scenarios that we will see. There are scenarios more complicated than this that involve multiple objects, which will each have their own diagrams that have to be drawn separately, and you'll have multiples of the same type of force, like you'll have two ropes, which means you'd have to label your tension forces, tension 1 and tension 2, and stuff like that. So we will see more complicated scenarios than this, but the point is, let's make sure we understand our various forces and how we can tell whether or not each of those types of forces is present. Just get in the habit of just mentally going through that checklist of the 7 forces that I had at the top of this document. Just go to, let's see, go to here and just mentally get in the habit of going through this whole list. The good news is for the 2 friction forces, you'll only ever have 1 of each type per surface. I should mention that if there's more than 1 surface, then there can be more than 1 friction. But for each surface, it can't be both static and kinetic. You'll have either static friction or kinetic friction per rough surface. So that simplifies things a little bit. You can condense 3 and 4 into a single category if you want. And let's see, what else? Well, normal force and the 2 friction forces require contact. Those are contact forces. So if there is no contact, then you can immediately rule out all 3 of these in one go. So that's an observation that might be helpful. And I think spring force and tension force are pretty obvious because, you will see that there's a spring or a rope or chain or whatever in the problem. So I don't think that one's going to be easy for a lot of people to miss. I think most people will just remember that just fine. Applied force, the problem statement will literally tell you when it's there. And I guess maybe sometimes people might forget the force of gravity. But get your diagrams right. Make sure you know which forces are present when. And if you are looking for this, you can either just take a screenshot right now of this frame, or you can go to the course plan, again linked in the description, and go to right here under practice, free body diagrams for Unit 3. If you go to this, that will get you that PDF. Okay, let me see, is there anything else I have opened here that we can play around with? Okay, I see one-dimensional force problems. We will get back to that. Let's... Actually, let me think. Do I want to continue here, or should we call it a day? Okay, let's talk about one-dimensional force problems so that we can actually have some math and some ability to do some practice problems. Yeah, let's do that. But before that, I need to talk about the normal force. I should have prepared this ahead of time, but let me see if I can find it. Ah, there it is. Okay. Here you have a bathroom scale. Now, some people will tell you that this thing measures weight. And those people are kind of right, but also kind of wrong. Because, well, if I put my hand on it like this, what is it measuring? Is it measuring the weight of my hand? No, maybe if I relax my hand on it. But if I'm just pushing on it deliberately with my fist, that's not the weight of my hand. What is it measuring? What is this thing measuring? This thing is measuring the amount of force that's being exerted on it. The way these things work typically is they have some springs inside of them, and based on the distance that those springs get pushed in, that will then push this needle. There's probably some sort of mechanism in there that gets pushed. And the neat thing about springs is that the amount of force applied to them is directly proportional to the length by which they are stretched or compressed. In fact, let me grab another physics toy. Where is it? Oh, there it is. This thing is kind of old-fashioned. Nowadays we have digital versions of these. Oh my goodness, and the lighting is not very helpful there. But you can probably see there towards the top it says 2.5 newtons / 250 grams. And then you've got, all these markings in newtons on one side and in grams on the other side. And you see they're not exactly lined up because, well, are they? Oh, I guess they are exactly lined up. No, they're not. That's just the zeros, which makes sense for them to be lined up. But you see, like, the 250 mark is a little bit higher than the 2.5 Newton mark because 2.5 newtons is actually a little bit less than 250. We will learn why later, but basically it's because G is 9.8 instead of 10. Actually, I can just tell you right now. The weight, the force of gravity on an object near Earth's surface is just the mass of that object times G. So for a 25 gram object, you would do 25 grams, I guess convert it to 0.025 kilograms, and then multiply it by 9.8, and you would get the equivalent of that in newtons, and it would be slightly less than 0.25 newtons. Anyway, here you notice that if I double the weight, if I go from, let's see, if I pull this all the way over to, if I pull this to the 100 gram mark, which is going to have a weight of like, what, 0.98? If I pull this thing to the 100 gram mark versus the 200 gram mark, you notice that it's length proportional. The 100 gram mark is exactly half as far of a stretch of the spring as the 200 gram mark. So this is why spring scales are a very useful tool for measuring the force acting on an object. It's convenient because of this proportionality. You know just from how much length it stretches or compresses, how much force is being applied. And of course, nowadays we have digital devices with stronger springs that can stretch for a much longer length with a much higher force tolerance. So this thing can stretch, what, like maybe 6, 7, 8 centimeters for about 2.5 newtons, but you can have springs that are much stronger and will only stretch a couple millimeters for maybe a couple dozen newtons. And we've fine-tuned it to the point where we can actually measure those really, really tiny millimeter or even fraction of a millimeter stretch to calculate those smaller forces more precisely. So yeah, springs are a pretty good mechanism for measuring force, and objects like this will either rely on compression or stretching of a spring to measure the force exerted on an object. So this is reporting what? It's not necessarily reporting my weight. It would report my weight if I was standing still on it, but like I showed earlier, if I just press on it, what it's showing me is the amount of force that I'm exerting on it. And that has to do with Newton's third law. We will discuss Newton's third law in more detail in a future stream, maybe next time, but probably not for a while. Actually, probably not for a while, because there's a lot we can do with Newton's first and second laws before we want to grapple with Newton's third law. But basically, if I'm pushing down on it and I'm getting a reading of 40 pounds, then I'm applying the equivalent of 40 pounds of force. Pounds actually are a unit of force, interestingly enough, but they're not our favorite unit of force, so you'll have to convert that to newtons. You can look up the conversion factor on Google. But anyway, so normal force doesn't actually have an equation. That's what I'm trying to get at here. And also, normal force does not equal weight. Those are two things that a lot of students misunderstand about the normal force. Normal force does not have an equation associated with it. There is no equation, there is no formula. There is no formula. There is no formula. Take this with you to the grave and fight anybody who dares to contradict this statement. There is no formula for normal force. Three exclamation marks. There is no formula for normal force. What else do you want? Quotation marks, italics, bold print. How many ways do I have to emphasize this? How many? Okay, maybe I'm exaggerating a little, but it's really important. There are a lot of misconceptions surrounding the nature of normal force. There is no formula for it. There is no formula for it. Some people will tell you that normal force equals mg. Wrong. Wrong, wrong, wrong. That relates to Newton's second law. So mg, I just mentioned it a little while ago, that's actually the formula for the force of gravity. The force of gravity on an object is equal to the mass of that object times the acceleration due to gravity, at least when you're close to the Earth. When you're farther away, you would use this formula, and we will ignore the existence of this formula until a later chapter. But for now, for flat Earth physics, force of gravity is equal to mg, and of course if you're not on Earth, then you would use whatever value of g you have on that other planet or moon or whatever. For example, on the moon, g is 1.6. You would just use your weight on the moon as your mass times 1.6, or whatever the g happens to be where your object is at. So a lot of people will mistakenly assume that normal force is equal to mg always, but that's not true. Where this myth comes from is a common scenario, which we actually saw in some of our diagrams, where an object will have a normal force opposing a gravitational force, and there are no other forces other than the normal force and the gravitational force along that direction, in this case, along the vertical direction. In this case, in order for Newton's second law to work, the normal force has to equal the gravitational force, because we know, just from common sense, you've never ever in your life pushed a box along the ground and seen it magically accelerate upward into the air or downward digging a hole into the ground. That just doesn't happen in real life most of the time. So we know that the acceleration in the vertical direction, net force in the y direction, must be equal to mass of the object times the acceleration of the object in the y direction. Well, the acceleration in the y direction is 0. We can just see that through common sense. So in this type of scenario, we would say the net force would be, I guess, forces upward minus forces downward. Normal force minus force of gravity. That's our net force along the y direction, is equal to mass times 0 is equal to 0, which would tell us the normal force is equal to the gravitational force, which then tells us that the normal force is equal to mg, but only for this kind of scenario. Only for this kind of scenario. So I'm going to give you something that you can do that will let you just feel the normal force happening. Let me go grab, what can I grab? Let me grab that book over there. Okay, so here's a book in my hand. And yes, I am trying to study Japanese. Now you've learned something about me. Anyway, so if you grab a book, and maybe you should pick up like a textbook, something with some heft to it so that you can feel the changes. Maybe this book that I chose wasn't the best example. But if you grab a book, right now your hand is exerting a normal force on the book, and you can feel it because the book is exerting the same amount of normal force on you. But what if a second person comes and they apply a little bit of force upward, not enough to lift the book out of your hand, but, just a little bit. What happens? The book feels lighter. Did the weight of the book change? No, its mass didn't change. The acceleration due to gravity didn't change. We didn't teleport to another planet all of a sudden. What is that change you're feeling? That's a change in the normal force. Now that there's some force upward, the normal force that your hand has to apply on the book doesn't have to be as high. The normal force that your hand is applying on the book needs to be just enough and only enough to prevent the book from accelerating downward. Your hand is applying a normal force upward in the first place in order to prevent this from happening, in order to prevent your hand from falling and slamming into the table. If I put this book on the table exerts a normal force upward on the book, because if it doesn't do that, then the table is going to get crushed and have a book-shaped hole in it. Normal force is basically objects trying to not get crushed under whatever force is being applied to them. And of course, there's a limit to that. If I sit down and I put some boxes on top of myself, I won't get crushed unless the boxes are really heavy. If I sit under, a bulldozer, I'm probably not going to survive that. My body has a limit to how much normal force it can exert outward before it just breaks down. So there is no actual formula for normal force. Normal force equals whatever it needs to equal, if that makes any sense, up to a limit. Normal force doesn't have a formula. Normal force is an inequality. Normal force is less than or equal to some sort of maximum normal force, which I guess you could call the durability of the object. The durability of... Why is that flickering? Oh. It'll settle down. The durability of the surface or the object that's in contact with your other object. Normal force is less than or equal to some sort of maximum. Usually this maximum will not be given to you. Usually it will just be assumed that whatever problem you are given, this maximum is high enough that the normal force can be whatever value you calculate that it needs to be. But that's really all there is to it. There is no formula for normal force. There's only an upper limit for how high it can go, and other than that, it can be as low as 0, so I should probably expand this inequality, put a 0 in there. So normal force is between 0 and some maximum. There's no such thing as negative normal force because surfaces can only push, they cannot pull. But there you go. Normal force equals whatever it needs to equal to fulfill the physical situation that is being presented to you in your book problem, or even just in your real life application problem. Normal force equals whatever it needs to equal. So going back to the case of the book with a person trying to lift it up, or in fact, if the person tries to push down. Either way, if another person or object or whatever, if another vertical force is exerted on this book while you're trying to hold it still, then you will experience a shift in the normal force. It will differ, either increase or decrease, in comparison to the book's actual weight. So if I were to draw that on a diagram, it would look like this. So here's the book, and then I guess here's a surface representing my hand holding the book. And then if I were to draw the diagram of this thing, let's say we've got, of course, normal force would have to be upward. The weight of the book has to be downward. And then I can either apply a force upward or downward. Let's say upward, for example. Let's say I apply a force upward. Let's say some other person comes in and applies a little bit of force upward, not enough to counter the full weight of the book, but enough that I experience a lower normal force. What happens then? Well, if the book is still sitting still in my hand, then the vertical acceleration is still 0. So net force in the vertical direction equals mass times acceleration in the vertical direction. Acceleration in the vertical would still be 0, so net force in the vertical would be 0, which means force is up minus force is down, normal force plus force applied minus force of gravity equals 0. If I try to solve this for the normal force, I add force of gravity to the right and subtract the force applied, and I get normal force equals force of gravity minus whatever this applied force is. So if the book weighed, for example, let's say 20 newtons, that's probably too much. No. Let's say 2 newtons. Let's say the book weighed 2 newtons. And then somebody applied a force of, half a newton upward on the book. Then the normal force that I exert on the book and that the book exerts on me would only be 1.5 newtons, which is less than the weight of the book. If the applied force were in the opposite direction, you can follow this math and just redo it. The only difference would be that the force applied would be down, so this would be a minus here, and then it would become a plus when you move it to the right. And in that case, the normal force would go above the weight of the book. So yeah, let's not adopt this false belief that normal force is equal to mg and sue anybody who tells you otherwise. Okay, maybe you can't afford to sue them, but I wish I could. Oh, I wish I could. The sad thing is that you see teachers rely on this idea. Like teachers who are teaching, some sort of basic level physics where the students won't have to deal with situations where the normal force is different from the gravitational force, I don't think that justifies it. I mean, if you could at the very least say, hey, this equation is true only for the scenarios that you're going to see in class. If you take other physics courses, you'll see scenarios where this isn't true. If you could at least say that, I'd be fine with it. But I've seen like videos and I've seen like assignments from students and stuff like that that just assumes this to be universally true. And it just gets on my nerves. Anyway, rant over. Let's talk about what's next. What is next? Let me think here. So that's normal force. Do we need to talk about tension force? Let me see. Can this one be done? Okay, we do need to talk about tension force. So tension force is kind of similar to normal force, except it works in the opposite direction. Tension force also does not have a formula. Tension force also does not have a formula. Tension force also just has an inequality. Tension force also just falls between 0 and some sort of maximum tension, which again you could call the durability, or sometimes I've heard it referred to as the breaking strength of the rope or chain or whatever, or tensile strength. Some sort of upper limit where if you pull too hard on your rope or string or whatever, it just snaps. But outside of that, as long as you're not hitting that limit, the more the need for tension increases in the problem, the more the tension will just increase and keep up with and adapt to the situation on the fly. So really, to calculate things like normal force and tension force, you need to actually do some math here. You need to apply Newton's second law and sometimes use a little bit of common sense to figure out what the acceleration needs to be, and then from there calculate, once all other forces are accounted for, calculate what would the tension need to be, what would the normal force need to be for these equations to be true, for this object to move the way that the problem is telling me it's supposed to move. Okay. And now that we've spoken about that, let's actually do a couple of problems before we wrap up for today. So I'm going to focus on just one-dimensional problems for now because working with one dimension is easy. We'll deal with the two-dimensional problems later, most likely next time. So I have for you elevator problems. And it says there, assume g equals 10 meters per second squared for all problems below. I'm going to go ahead and do that because I'm pretty sure I picked the numbers in here to actually work really well with 10 for g. So this is one of those rare instances where I'm actually going to use 10 for g. Okay, so formulas, we've already seen all this. Gravitational force equals m times g, we already spoke about that. Let's go ahead and look at what we have here. So number one says a block is sitting on the floor of an elevator as shown. It's a 50 kilogram block, and it says find the normal force on the block when the elevator is stationary, when the elevator accelerates upward at a rate of 5 meters per second squared, when the elevator moves upward at a constant speed of 3 meters per second, and when the elevator accelerates downward at a rate of 4 meters per second squared. And then there's a bonus question, is it possible for the block to accelerate downward at a rate of 15 meters per second squared? And if not, what is needed to make that happen? I'll probably skip that, but we'll see. Okay, let's do that first part. So I'm probably going to need a new sheet really soon. In fact, oh, wait, I've got the backside of this sheet. Okay, we're good. So we've got ourselves an elevator here. And inside this elevator, we've got a 50 kilogram block. Okay, let's draw the force diagram for this thing. So it says, find the normal force on the block when the elevator is in, well, we'll deal with that when we get to it, but the diagram shouldn't change for any of those scenarios. The normal force should always just be upward. The force of gravity should always be downward, not drawn to scale, because in some of these cases the normal force will be larger and in other cases it will be smaller. So this vector diagram is not to scale. And yeah, those are the only forces at play here. Normal force upward and gravitational force downward. And I'm going to just go ahead and state net force in this case is going to be, I'm going to define up as positive, minus, I'm going to define down as negative, and we're going to have that net force is also equal to mass times acceleration. So normal, whoops, not like that, normal force minus mg is equal to ma. Normal force minus the mass is 50, and for g I'm using 10, is equal to the mass again is 50, and for the acceleration that will change from one part to another. So part A says, find the normal force on the block when the elevator is stationary. That means it's at rest and also not accelerating, which is the more important thing. So part A, when the acceleration is equal to 0, basically. Well, when the acceleration is equal to 0, you're going to get normal force minus 500 equals 50 times 0, well that's 0. So you get normal force equals 500 newtons. And we're done. It just equals the weight of the block in scenario A. That's about to change. Scenario B. It says for scenario B, let me put that up on the screen again and let me zoom it in. Scenario B, the elevator accelerates upward at a rate of 5 meters per second squared. So I said up was positive for this problem, so let's use positive 5 for our acceleration. What color do I want to use? Let's use pink. I haven't touched you in a while. So this time acceleration equals positive 5 meters per second squared. In that case, we're going to have normal force minus 500 equals 50 times positive 5, which is positive 250. Add 500 to both sides. Normal force is equal to 750 newtons. And this makes sense. If I look back on my diagram, 750 up and 500 down, yeah, it makes sense that I should have more force upward than downward if this elevator and everything in it is supposed to accelerate upward. So that's making sense. Okay, part C. Part C says the elevator moves upward at a constant speed of 3 meters per second. Some people might already know what the trick is with this one. So first off, it says constant speed. That's only telling you the magnitude, but it did tell you that the elevator moves up, so you also know the direction. So the magnitude is constant and the direction is constant for the velocity. We have a constant velocity. What does that mean? Constant velocity. Well, that means the acceleration is 0. And if the acceleration is 0, we're basically just going to get the same result as part A. We're going to get normal force equals 500 newtons. No need to redo the math that we did for part A. We can just copy the result. When the acceleration is 0, the normal force is just going to be equal to the gravitational force in magnitude. Okay, and part D, the elevator accelerates down at a rate of 4 meters per second squared. Okay, down is going to be negative, so -4. So part D, I'm going to use acceleration equals -4 meters per second squared. And that will give me, I'm going to do normal force minus 500 equals the mass, 50, times the acceleration, -4. And that's going to be -200. Add 500 to both sides, and you get normal force equals -200 plus 500 is positive 300 newtons. And yeah, 300 newtons up versus 500 newtons down. There's more down than up. Acceleration is down. That all adds up. That makes sense to me. So there we have it. I guess we can look at that bonus question real quick then. So the bonus question was, is it possible for the block to accelerate down at a rate of 15 meters per second squared? So if I plug -15 into my equation, I'm immediately going to run into a problem. It says, if not, what is needed to make that happen? So if I were to plug -15 in here, what would happen? Well, -15 times 50 would be -750. And if you add 500 to both sides, -750 becomes -250. So you would need a normal force of -250. But normal force cannot go that low. Normal force, that would mean that the normal force would have to pull the block downward. But the floor of the elevator cannot pull. It can only push. It can't go any lower than 0. So this is not realistic. What would need to happen is, well, the normal force would be all gone. It would have to go as low as it can go, 0. And then on top of that, you would need to have some sort of applied force downward. Or if you're feeling really dangerous, you can assume that the elevator accelerates down while the block doesn't accelerate down as much. So the elevator is going down faster than the block. So over time, it will appear as if, to someone in the elevator, it will appear as if the box is slowly but surely floating up. Not because it's actually floating up, but because the box is falling slower than the elevator, and eventually the box will end up touching the top surface of the elevator, and in that situation, you'd have the force of gravity acting downward, and now the surface of contact is on the top. The normal force between the ceiling of the elevator and the block would be downward, and then the block would get that extra 250 newtons downward and continue with the elevator from that point on. This is all assuming, of course, that the elevator is falling far enough and long enough for this to happen. The elevator would have to start from pretty high up for this to work, but there you go. That is one way for this situation to be possible, but otherwise, no, you can't fall faster than the acceleration due to gravity without some sort of additional downward force. All right. Now, which of these do I want to leave as an exercise, and which do I want to do next? I think I will do number 2 next. So 2 deals with a situation where we have to consider 2 objects instead of just one. Up to this point, we've only been diagramming a single object, and now we're going to do two objects. So for two objects, you're going to need two diagrams, and you're going to need two net force equations. So let's see. It says the elevator from the previous problem is supported by a cable as shown. If the elevator itself has a mass of 500 kilograms, find the tension in the cable when the elevator is stationary, when the elevator accelerates upward at a rate of 5, when the elevator moves upward at constant speed of 3, and when the elevator accelerates downward at a rate of 4. Those numbers might look familiar. That's because they're the same numbers we used in that first problem. The hint even says you will need to use your answers from the previous problem, so it's a good thing that we did that. Okay, let's see what we can do here. So I drew a diagram for the 50 kilogram object. Now I'm going to draw a separate diagram for the elevator itself. So what does the elevator have acting on it? The elevator will have, well, there's a cable that can only pull up on it, so force of tension upward. And then the elevator itself is 500 kilograms, so I'm going to go ahead and write that. And then the elevator, of course, has a weight, so the earth is pulling on it. There's a force of gravity. And there's also one more force. This elevator is touching something. It's touching the block. It's touching the box that's inside of it. And if the box is above the bottom of the elevator, then the normal force that the box exerts on the elevator has to be downward. And Newton's third law, the magnitude of this normal force will be equal to the normal force that the elevator exerted upward on the block in each of our 4 scenarios. So whatever normal force we calculated for parts A, B, C, and D, that's exactly what this downward normal force on the elevator is going to be. So we will know this because we calculated it before. We will know this because it's just multiplying by G, 500 times G, and that leaves us with just the force of tension would be the only unknown left. So yeah, this is very doable. So let's look at case A, where the acceleration is equal to 0. That means that, well, I guess I should write it over here. So net force on the elevator is equal to the mass of the elevator. I'll use capital M for the elevator so that we don't confuse it with the box, times the acceleration of the elevator. So net force on the elevator is forces up minus forces down. I'm using up as the positive direction again. So force of tension minus normal force minus force of gravity, big M, times G is equal to big M times A. That's what I have. So that's going to be force of tension minus whatever normal force I got for the box minus 500 times 10 is equal to 500 times A. Okay, now we can use this over here. So we've got force of tension minus, what's the normal force when the acceleration is 0? It was 500. So minus 500. And also minus 500 times 10, so minus 5,000. Equals 500 times 0, which is just 0. Okay, so in this case, add 5,000 and add 500 over to the right. The tension force in the cable must be 5,500 newtons. That cable better be made of, like, I don't know, steel wire or something. Because, yeah, it's got a lot of lifting to do. Okay, part B. This time the acceleration is positive 5. Oh, I forgot to put my... Man, I was doing so good too, remembering to flip back and forth between the camera and the... Sorry about that. Anyway, I drew the diagram for the elevator. I wrote all this stuff. Net force equals the mass of the elevator, which I just called big M, times the acceleration. Substitute net force with forces up minus the forces down equals ma, and then I just made substitutions for the numbers we know so that we can just skip straight to calculation. And yeah, we'll talk about part A again. So when acceleration was 0, just copying this, force of tension minus the normal force we got was 500 newtons from before. And then minus, of course, the 5,000 is equal to mass times acceleration would have been 0 there, and that's how I got force of tension equals 5,500 newtons. Okay, now we're all caught up on the stuff that sadly was not on the screen while I was doing it. Back to part B. Acceleration is positive 5 meters per second squared. That will give us, writing this equation, force of tension minus what was the normal force in the second scenario. In the second scenario, the normal force was 750. So if 750 newtons were exerted upward on the block, then 750 newtons were exerted downward on the elevator. Minus the 5,000 again equals 500 times positive 5. 500 times positive 5, which would be 2,500. So we've got 2,500 plus 5,000 is 7,500. And then 7,500 plus 750. 7,500 plus 700 is 8,200, and then 50 more, so 8,250. If my math is right, force of tension would have to be 8,250 newtons to pull this thing upward. And yeah, that makes sense. When you're pulling up, the tension should be greater than when you're not accelerating up or down. Let me just double check with my calculator and make sure I didn't screw something up with my mental math. 500 times 5 plus 5,000 and plus 750. Yep, 8,250. Okay, just double checking. Part C, let's switch to another color. Part C, oh, actually, we can skip part C because part C is when you have a constant velocity, which is going to be the same as when your acceleration is 0. Part C, we're just going to get the same scenario we got for part A. Force of tension would be equal to 5,500 newtons again. Okay, so that part's done. And part D. Is that still visible on the screen? Yeah. Part D, we would have an acceleration of 4 downward, so acceleration equals negative 4 meters per second squared. That gives me force of tension minus the normal force when the acceleration is negative 4 is 300 newtons, so minus 300, and also minus the weight of the elevator, 5,000 again, equals 500 times negative 4. So that's going to be negative 2,000 on the right, add 5,000, and that becomes 3,000, and add 300, the tension force in this cable would be equal to 3,300 newtons, and that makes sense when you're trying to let the elevator down. The cable doesn't have to pull up on it as hard. It still needs to pull up on it so that it doesn't fall too fast, but should be lower than the force required to just keep it steady. Should be lower than 5,500 newtons. Okay, and I think that is where we will have to wrap things up. So for homework, there's still parts 3 and 4 over here. They're basically the same thing, except I'm replacing the normal force with the tension force, but otherwise it's all going to work pretty much in the same way, where for problem 3, you'll calculate the tension force needed to get whatever acceleration, and then for part 4, whatever that tension was pulling up on the block, an equal amount of tension will pull down on the elevator. And yeah, it's basically the same problem, except replace the normal force with tension force that essentially has the same function. And then for the next one, you just do it all in one problem. Instead of having the block in one problem and the elevator in another problem, this next exercise puts both of them all in one problem, all in one go, and also has a horizontal problem that will get you thinking in 2 dimensions. My hint for this one is calculate the net force vertically, separate from the net force horizontally. Actually, no, skip this one because we haven't talked about the equation for calculating friction, so never mind. Skip number 3 if you get to this. We haven't learned how to calculate friction yet, so yeah, just 1 and 2 if you open this. And these can be found on, again, the physics course plan, linked in the description. If you scroll down to force and go to practice, you've got 1D force problems, and then the next one is the one titled More Vertical Force Problems and the Intro 2D problem. So that would be this one. If you want to do it, you can just skip number 3 because we haven't learned that yet. Unless you've already learned friction for yourself, then you're more than welcome to try it out. But yeah, other than that, what else do I want to recommend for homework? Well, we do have the Chapter 4 conceptual questions and problems and exercises. You can probably do some of them now with what we've covered for today, although probably not that much because I imagine a lot of these are going to be 2-dimensional problems. So yeah, I think you might be better off just practicing with the PDFs for now. But definitely go back to this one with the free body diagrams and see if you can redo all of this by yourself, because this is crucial. Getting your diagram right, just making sure you have all the forces present and drawn in the right direction is the most important thing before you do any sort of calculations. And I think that is all I have for recommendations. Videos and resources, is there anything? If you didn't look at this one, now would probably be a good time to look at it. Also, probably you want to introduce yourself to friction. Let's see. Spring forces we can leave for a while. And we don't have to worry about pulleys just yet. I'm probably going to be covering problems where you have like multiple blocks connected by ropes but without pulleys just yet. That's going to be the plan for next time. Maybe we'll have time for pulleys at the end next time. I'm not entirely sure. But at the very least, we've covered the basic ideas behind normal force and tension force. Applied force is just kind of, whatever the problem tells you, you don't have to do a lot of thinking for it. So next time we will have to talk about friction in a little bit more depth. And spring force, I'm not sure when I want to talk about spring force, because the thing with spring force is that it becomes more important much later. There's not much interesting stuff that we can do with it right now. But I'll think about it over the weekend. We'll figure something out. Okay. For traditional office hours, I think what I'm going to do is just postpone that until tomorrow. And this time I'm actually going to try and schedule it in the YouTube Live thing, whatever it's called. But my plan for traditional office hours, for those who are interested, will be just doing a couple more applications of Riemann sums. I want to calculate like the moment of inertia formula for a solid sphere, and I want to do like how to calculate the volume of what's called a spherical cap. I just found out today, where you take, let me grab my sphere, or well, my half sphere, and basically if you just cut it horizontally so that it's no longer a perfect half sphere, I'm thinking of doing some calculus to derive what the volume formula for that thing would be, to answer the question of how high do I need to fill this thing with water in order for the amount of water in it to actually be half of the total capacity that it could hold. And it's definitely going to be higher than the halfway point if you think about it. So yeah, I'm interested in the calculus of that, so look forward to that tomorrow, hopefully, unless I encounter technical difficulties or whatever. But that is it for today. Hope you learned something useful. Take care, and I will see you guys tomorrow or next week, depending on what you were here for. See ya!